Hello everyone. So, this is Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. So, I will be the TA for this course, Essentials of Topology. So, this is a 12-week course. That means there will be 12 live sessions, and this is the first one. So, in this live session, I'm supposed to solve some problems and answer doubts if you have any. So, if you have any doubts, just feel free to ask. And so, first of all, I will just summarize the contents of first week. Then I will start solving some problems. In between, if you have any doubts or questions, you just unmute yourself and ask. So the first week is basically recalling some other known things. So we started with basic theory of sets and functions that we will need in this course. And after that, we we did the basics of metric space theory, just definitions and some examples. So in metric spaces, we give the definition, we give some examples, and also we define what do we mean by open balls and open sets. Then using this concept, we have generalized this notion to the notion of topological spaces. And we gave the definition of topological spaces and two or three examples we have done. We will see some more examples in the upcoming lectures, but this is the overall contents of the first week. So if you have any doubts among these topics, so you can just raise your voice. So I have picked some problems among the tutorials. So it will help to do the tutorial problems. So let's see them. So I will mostly do based on metric spaces and topological spaces because the other parts are school level mathematics. So, okay, so let's start with the first one. So let X be a non-empty set and let's take three metrics on X. Let's say D1 and D2 be three metrics. Okay, so using these three metrics on X, we can construct some more metrics. So I will just list those things because it will be useful to keep record, because some of the questions can be done from this record only. So the first thing is, okay, let me say this is A. The following are metrics on X. So the first one is let's say d prime of x comma y, this is defined as minimum of some a comma dxy, where x comma y belongs to x and a is, okay, not a, let's say it's r, and r belongs to open interval 0 to infinity, some fixed real number. So instead of r, you might be seeing it's 1 in most of the cases, but it will work for any positive real number. Okay, the second one is, let us define d double prime of xy as square root of dxy, where xy belongs to x. So this will also be a metric on x. And third one is, let's say d triple prime of xy, and it is defined as d of xy divided by 1 plus d of xy, where x and y belongs to x. So all these things, most of the cases you might have known, but let's keep this thing in one place. Fourth one is, okay, let's say e of xy is some a times d of xy, where a is a fixed positive real number. Okay, so this is the fourth one. Let's do some more. Let's say e prime of xy is just sum of d1 and d2. So d1 of xy plus d2 of xy. And let's say the sixth one, e double prime of xy, and how it is defined? It is basically maximum of d1 xy comma d2 xy. So for the timing, let's keep this 6 metrics, and some of the functions which are not metrics. So the following, need not be a metric on x. And what are they? So see, from this list, so first one you can see I have defined in terms of minimum. So if I replace the minimum, is it still a metric? So that we can ask, and you can see, or you can prove that it did not be a metric. So how to write that? So I am just writing as maximum of 1 comma d. This need not be a metric. Second one is, so we have taken square root, right? So what happens if we take some other power? So let's take d square. So we can see that d square need not be a metric. And so this is just positive scalar multiplication, and this is sum. So instead of sum, if we take, let's say, difference, then what happens? Then we can say that it also need not be a metric. And here, in term, if we replace the maximum by minimum, then also that one need not be a metric. Okay, so this is the more more or less which I want to mention. So among these, you might have seen all the proofs, but let me do a few of them because okay, so maybe I will do those things which you may not get in all the books. So maybe the first one, I think it is more or less there in all of the books. Maybe I will do the second one, and fourth one is very easy. So second and third, maybe first I will do. So the second one, it is just square root. Okay, so to prove this one is a metric, we need to check three axioms. So I am just writing those in the side in this case. So what we have to check that d prime xy is always non-negative for all xy, and d prime xy is 0 if and only if x equals to y. So this is one part. This is the first axiom, non-negativity. Second one is you can recall it is symmetry. So d prime xy is d prime yx. Distance from x to y is same as distance from y to x. That is also for all xy. Third one is the most important, is the triangle inequality. So d prime xz is basically less equals to d prime xy plus d prime yz, and this is for all xyz in x. So we need to check these three axioms. So let's check one by one. So what about the non-negativity of this square root function? So this is clear, right? Since this is the positive square root, so this is also non-negative. So since dxy is non-negative for all xy, so the positive square root is also non-negative. And so square root of dxy is 0. That is true if and only if dxy is 0. But d is a metric. So this is true if and only if x equals to y. So the first axiom you can check easily. Now the symmetry. Symmetry is also trivial. So square root of dxy is basically same as square root of dyx, because d is a metric. Now we need to check the triangle inequality. So now we need to prove square root of dxz less equals to square root of dxy plus square root of dyz, and this is for all xyz in x. Okay, so this is the thing we need to prove. So any idea how to do it? Just try to think how to prove this. Yes, anyone? Sorry, have you give any answer? I am not able to hear you.
Since dxy is a metric they are already given,
Yes.
taking that with the help of since it is a metric, we can take that directly inequality.
Sorry, your voice is breaking, I think.
Sir, since d is a metric they are already mentioned in the top, we
Yes.
can directly take the triangular inequality and
Yes.
applying a square root. Square root of a plus b is less than or equal to square root of a, so it will, I think it will divide, plus will going to become break, hence the equality is going to hold.
So you are saying square root of,
Yeah, plus b is less than or equal to square root of a plus square root of b. I think this is not my true. That is where I'm getting some mistake.
okay, so let's see how to do it. So what we know is, we need to prove this for all xyz. So let's pick some xyz. So let xyz belongs to x. Now since D is a metric, so we can write dxz is less or equals to dxy plus dyz, right? So now this thing is less equals to dxy plus dyz plus 2 times square root of dxy times dyz. This we can do, right? Because this is a non-negative number, we are adding this. So this is less equals to. But what is this thing? This is basically square root of dxy plus square root of dyz, and you take the whole square. So basically what we are getting is square. So left hand side we can also rewrite as this one. So this is less equals to, so we are getting the square root. So now we can take, sorry, we are getting the square. So what we need, we are getting the square of this. So just take the square root. So this will imply dxz is less equals to square root of dxy plus square root of dyz. And that is what we wanted to prove. So just easy observation, it's nothing much difficult. So this proves the triangle inequality. So I hope this one is fine. So I proved the second one. Let's the third one, I think it is also there. Okay, maybe let's do this because the triangle inequality you might face some problem. And this one is important. I will use this metric again in the upcoming problems. Let's spend some time on this. Okay, so the third one is d triple prime xy. It is defined as d over xy plus 1 over d of xy. So we need to prove this one is a metric. So the non-negativity part. This part is easy. So dxy is positive. So 1 plus dxy is bigger equals to 1. So d xy over 1 plus dxy. This is also clearly non-negative. And d triple prime xy is 0. So this will be 0 if and only if the numerator is 0. So that is true if and only if dxy is 0. And since d is a metric, so this is true if and only if x equals to y. So this part is more or less trivial. So non-negativity is done. Now the symmetry. So d double prime xy is basically d of xy by 1 plus d of xy. Now use the symmetry of d. So this is d of yx by 1 plus d of yx. And by definition, this is d triple prime of y comma x. So this is also trivial, but the non-trivial part is the triangle inequality. So let's try to prove this. So let's take 3 points from the set X. Now let's see what we have to prove. So we want to show d triple prime xz is less or equals to d triple prime xy plus d triple prime yz. And what is this thing? This is basically d over xz by 1 plus dxz less equals to dxy by 1 plus dxy, and this is dyz by 1 plus dyz. This thing we want to prove, and what we have. So now, since d is a metric, we can use the triangle inequality of d. So let's use that thing. So then d of xz is less equals to d of xy plus d of yz. So this thing is given, and this is what we want to prove. So any idea how to do this? Okay, so let's focus on this left hand side. Okay, so this dxz over 1 plus dxz, how to write this? Uh, so this is basically we can replace the top. So dx comma y plus dy comma z over 1 plus dxz. But this is dxy over 1 plus dxz plus dyz over 1 plus dxz. So now uh, so basically we can use these identities. Okay, so we need to use two identities. This is the first one. Let's say this is true for all AB non-negative, and the second one is this function x over 1 plus x. This is non-decreasing, means it is monotonically increasing. So if we use this thing, then okay, I think I need to modify this one. Yeah, so let's use the non-increasing, sorry, non monotonically increasing thing. So this number is less equals to this number. So if you put f of x as x by 1 plus x, so monotonically increasing means what? So if x1 is less equals to x2, then f of x1 is less equals to f of x2. So apply that thing, as this is x1 and this is x2. So then we can write this is d of yz over 1 plus d of xy plus d of yz, right? And okay, we don't need this. Okay, now apply the second item, this one, a plus b by 1 plus a plus b is less equals to a by 1 plus a plus b by 1 plus b. So this is by the second item, this is by the first item. So maybe I will write this by 1 and this is by 2. But this thing is exactly what we wanted to prove. So we need to use these two facts. But I will not prove these facts, that you can check this. Yeah, so this gives the triangle inequality. So this is non-trivial actually, but we have done the proof. So I have proved the third one also. And the fourth one is just scalar multiplication by a positive real number, and this is very easy to prove, so I am just avoiding this one. And for the sum of two metric, that is also easy to prove, and maximum is also more or less easy. So just keep remember that if you take two metrics, their sum is also a metric, positive scalar multiplication is a metric, maximum is a metric, and here d by 1 plus d and square root. So this proves the metrics, and in the second part we have non-examples. So let's do the second part. Meanwhile, do you have any doubt? Okay, so if you have no doubt, let's move. So we need to show that maximum of 1 comma d, this need not be a metric. That means one of these three axioms it might not satisfy. So can you see which axiom it may fail for the first one?
Sir, the square root what you have done, is it
Yes.
going to hold for 1 by n? Means not only root to 1 by 3, 1 by something just like that. Is it hold for everything or only for root to metric? If you take any metric and if you apply its square root, then it will be a metric. What
Yes.
about it will be 1 by 3 or 1 by n? Something just n be
So
natural number.
I think the only problematic part is the triangle inequality. So whatever we have done here, I I don't think I think it work. I think it will form a metric. So you just try to prove the same thing using the binomial formula a plus b power n. So here we have used a plus b whole square formula. So if you use the other binomial formula, I think it will hold. Okay. So you just check
Okay.
the routine process, try to
Yes.
do the analogous
Yes.
calculations.
Okay. Okay, sir.
Yeah, yeah, that's a good observation that it will hold for other powers or not. Okay. So maximum of 1 comma d is not a metric. So you are checking that which axioms will fail. So any idea?
Just simply, sir, I'm going to take a d1 metric x equal to y. I will take d1 0 and d2. Here it will not hold, I think. So. Sorry, sir. Means
Uh,
maximum.
yeah, which axiom will fail? Yeah, others.
First axiom was one and
Sorry,
the
your
maximum.
voice is not clear.
So the first axiom will fail.
Yeah, exactly. The first axiom will fail. Yeah, correct. Okay, so let me write it down quickly. So for the first one, maximum of 1 comma dxy. So if you take x equals to y, then dxy is 0. So that means maximum of 1 comma dxy is 1. It is not 0. But according to our axioms, it should be 0. So the first axiom fails. So it cannot be a metric in general. Now what about d square? What about the second one? Which axiom may fail?
I think triangle inequality will fail.
Okay, yeah, you are correct, but can you give some explicit example? So, what is this? This is d square. So let's take d, the usual metric on R. So what will be then d square of xy, basically square of this, means this one. So let's take, okay, what to take? So let's say this is E. So this is EXY square. Sorry, EXY equals to this one. So let's say E02. Then what is this thing? Mm, this is basically 2 square. So this is 4. So so our x is 0, z is 2, and y is 1. So what is E01? This is 1, and E12, this is also 1. So E02 is actually bigger than E01 plus E12. So triangle inequality is not holding. Yeah, okay. Okay, so D square is not a metric. Now what about the third one? The difference of two metrics. This one is easy, right? Difference of two metrics. Yes.
So T1 minus D2 can be negative for someone.
Yes, exactly. It can be negative. Yes, you are right. So I'm not writing the third one because it's very easy. And what about minimum of D1 comma D2? So minimum of D1 comma D2, in general it is not a metric. In some cases it can be a metric, but in general it is not. Do you have any specific counter example? See, uh, one thing, if D1 and D2 are equal, then the minimum is just D1, right? Then it is a metric. So for counter example, you need to take some different metrics that you have to check. So I am also leaving this. I'm not doing this one. So you can check that minimum of D1 D2 is not a metric. I think it is there on the books also. So let's leave this. So third one you have already done. But if you are not able to do, you can come back again later in the next live session and try to answer. Meanwhile, you may try that time. Okay, so the first problem is done. So just try to remember at least which one forms a metric. The positive scalar multiplication, sum of two metric, maximum of two metric, d1 d over 1 by d. At least this type of things. Okay, let's move on. So based on this, let me give a quick question, and it appear on GATE 2026. So let X be a set with at least two elements. Okay, and let d1, d2, d3 be metrics on X. Then which one is not a metric on X? Which one is not a metric on X? So the first one is minimum of d1 comma 3. Second one is maximum of 3 comma d2. Third one is 10 d3 over 1 plus d3. Third one is 1 by 3 d1 plus d2 plus d3. So which one is not a metric in general?
Just square of the
Sorry, you can also write in the chat box if you are not able to. Speak.
T1 and T, first one.
First one is not a matrix.
Sir, second one is not a matrix. Since if you take d2 is 0, d of xy is equal to 0, the maximum will be
Yeah,
3. But
that
whenever d of xy equal to 0, it must be 0 only when x equal to 1.
yes, that we have already done just in the previous problem, right? So answer is B. But we have also proved that the first one is a metric in the first problem. But can you see that why C and D are metrics? Can you give some?
Yes, sir, it is just the previously what you have said.
Okay, so for
Metric
C,
upon
yes.
the same above what you have done. If you take any metric and if you scalar positive scalar multiple, it will be always metric. And 1 upon d3 is also metric.
Yeah, so D3 is a metric. So this will give D3 by 1 plus D3 is a metric. Now you just taking the scalar multiplication by 10. This is a positive number. So this will be a metric. And what about for the last one?
That is also follows the linear what is
Yeah.
addition,
So
linear
sum of
combination.
finite number of matrix is a metric, and you are taking a positive scalar multiplication by a positive real number. So all this follows from what we have done in the previous problem. So this one is a very easy problem, I think. So any doubts or questions?
No doubts, sir. Sir, how to read a textbook while listening the class at a time, and how to go through that whatever the references given by the NPTEL courses, how we should follow and how to
So how to? So I'm not able to
read the
understand your question.
how to read the references what were provided in the NPTEL course, and how to understand the means the concepts while reading it will be okay.
So you want the references?
No, I know the references, but how to read and how to apply this part while reading the question. At the same time, we are going to while we read the textbook, and if we have to apply that application part in the understanding the question, how it will be possible? I am asking.
Understanding the which question?
Means whenever we are going to read the textbook, the references, Adam columns, for suppose, while
Yes.
reading it will be okay, but how to read that textbook part and which part we have to focus more in the textbook?
So maybe I will suggest you first follow what they are teaching in this course, then go for the book. Then I think it will be easy to understand. But if you go directly to the book, I think it will be a little bit difficult, because if you just attend the lectures, so you already have some idea, right?
Yes, sir.
Then it
Yes,
will
sir.
be easy.
Mm.
Okay, any other queries? Okay, okay, just take you just give me 1 minute. Okay, let's move on to the next problem. So this is just a true or false type question. Okay, so let x comma d be a metric space. That means d is a metric on x. Okay, then uh, d over 1 plus 2026d is also a metric on d. Metric on x. Okay, so this is the problem. We need to check this one is a metric or not. So any idea or any answer?
True, sir.
How?
2026D is a metric,
Yes.
then 2026D upon 1 plus 2026D is a metric,
Yes.
then 1 over 2026 times that is a metric.
Yes. Yes. Correct. So this is true. This is also more or less easy. So 2026D by 1 plus 2026D is a metric. Now you just do this thing. So this is fairly easier. So let me give you one more exercise for you. Maybe you can try it later. That I'm not going to do now. So let D1 and D2 be two metric on X. Then check whether D1 over 1 plus D2 is a metric on X or not. Okay, just try to do this one. If you get some answer, you can also let me know. I think let's move on. So this is the fourth problem. So this is like if you have a metric space and if you have another set, and from that set to the metric space, if you have a function, one function, then how you will create a metric on your set. So let y comma d be a metric space and f from x to y be an one function, just a function. So then using the metric on y, we will define a metric on x, and this method is very much useful. You will see later also. If you have done a course on metric spaces, you might have seen this. Okay, then e from x cross x to non-negative real numbers defined by e of xy is basically d of fx comma fy is a metric on y. Okay, so the proof is I hope you have understood the statement. So you have a one function from a set x to another set y, and your codomain is a metric space, right? And you want to create a metric on the domain using that metric of the codomain. And this is the conventional or usual way. Uh, and you can check all the axioms will satisfy easily, but for the first axiom, non-negativity, to hold that axiom, we need the one condition. Only for that condition we need this oneness. Otherwise all the axioms will hold trivially. Maybe let me do the proof quickly because it will not take much time. Also, it's good to know the proofs. So e of xy is defined as d of fx fy, but d is a non-negative function, so this is non-negative. for all xy belongs to x. And E of xy is 0. This is true if and only if d of fx fy is 0. That is by definition. But d is a metric. So this is true if and only if fx equals to fy. And f is an injective function. So since f is an injective function, this is true if and only if x equals to y. So this proves the first axiom. So this is the only place where we need the injectivity of the function f. Now the symmetry, these things are fairly easier. So exy is d of fx comma fy by definition, and d is a metric, so d is symmetric. And by definition this is eyx, and this is true for all xy. So this proves the second axiom. So the last one is the triangle inequality, and that one will also follow in this case easily. So E of xy is by definition d of fx fy, and this is so we are taking 3 points from the domain d xyz belongs to x. So this is less equals to d of fx fy plus d of fy fz. This is true because of the triangle inequality of d. So this is E of xy plus E of yz. So right, here also nothing to prove much. So this gives the proof. Now let's utilize this one in our next problems. So what is the number? This is 4. Okay, meanwhile any questions so far?
In the last step for triangular inequality, it will be E of x comma z.
Sorry, yeah, you are right. Yeah, thank you. Yeah, anything else?
Sir, only codomain is required to be a metric space. What about domain? When if a domain is a metric space, can we say something regarding?
Regarding the codomain?
Means is since the codomain is a metric space, we are going to define a one function, and we have taken these things are going to hold.
Yes.
The same manner, if domain is a metric space, can we say is there any like that?
So see, if you take a metric on the domain and you want to create a metric on the codomain, first of all, you need to this function need to be surjective, because you need to use the preimage of the elements,
Yes,
right?
sir.
So that is one thing. And also in the similar manner, if you want to put the non-negativity part, I think you will need the injectivity. So ultimately you need a bijective function. And in bijective function, you take metric on the domain or in the codomain, I think it will not matter. Okay.
Okay. Yes, sir. Thank you, sir.
Yeah, if there is some other way than this, that I don't know, but I think this is the usual idea. So this idea is very natural, right? We are creating this metric in a natural way.
But here injectivity isn't necessary.
Yeah, injectivity
Yes.
needed here. Only
Yes, sir.
this part.
Whenever we have to take the domain, the bijective should be necessary condition.
For this problem.
Oh, sorry. Whenever domain is a metric space.
Yeah, in that case, if you want to do this in the same way, then we need bijectivity.
Okay, sir.
Otherwise,
Okay.
I don't know if there is any other way.
Yes. Yes. Thank you,
And
sir.
also, I want to mention one thing. If you do not assume injectivity of this function, then you will get something called pseudometric. So that is without this condition. So I hope you are.
Pseudometric means what? Is there any particular definition for that?
Yeah. So in the definition of metric, we have three axioms. And in the first axiom, there is also two part. So the second part will not hold for pseudometric, one direction. This is even only if. So for pseudometric, one direction is not true.
Okay, sir.
So
Yes, sir. Thank
can
you.
you might see
Yes.
the definition in the book. I think it is there in the
I
standard
think
text.
the word is not mentioned.
Yeah, I think it is there in some textbooks.
Oh, yes, sir.
But okay, let's move on to the next problem. So this one is from GET 2021. Okay, this is also fairly easier. So there is two statements. First one is P. It says d1 of x comma y defined as modulus of log of x over y. This is a metric on the set open interval 0, 1. So this is the first statement. Second one is d2 of xy. It is defined as modulus of x plus modulus of y when x is not equals to y, and 0 if x is equals to y. So they are saying this is also a metric on the open interval 0, 1. So there is two statements, and the first option is both pq is true. Second option is both pq false. Third one is p is true, q is false. And the fourth one is p false, q true. Okay, now, so we have to check these two things are metric or not. So let's focus on the first one. So d1 xy of modulus log of x by y. This is metric on this open interval or not? So any guess?
So log of x by y is in general will not be equal to log of y by x. So it is not effective.
Is it? But we are taking the modulus, right?
Yes, sir, it is a metric.
Okay, but how?
Because it is clearly non-negative,
Yes.
and distance between x and x equals absolute value of log x by x, which is absolute value of log 1, which is absolute value of 0, which is 0.
Yes.
And if absolute value of log x over y is 0, then log x over y is 0, which
Yes.
implies that x over y is 1, which implies that x equals 1.
Yeah, true.
And triangle inequality holds because log x over y equals log x minus log y.
Yes. Yeah, you are right. So it will be a metric. and the symmetry will follow because we are taking the modulus. Or what you can do is you can use the previous problem. Let me show how to do this. That problem is very much useful. So you take a function f from open interval 0 1 to r. How? F of x is log x. And you take r with the usual metric. And this function is 1 1 function. So it will induce a metric on the domain. So then basically d1 of xy is just f of how to write this, modulus of fx minus fy. This is modulus of log x minus log y. This is log of x over y. So if you just use the previous problem using this 1 1 function, you will get that d1 is a metric. Or you can check by the definition also. That is also very easy. You don't need to use any other trick. So P is true. So D1 is a metric. Now what about D2? Yeah, any guesses?
So it's also a metric because
Yes.
the next time is equal to y, then the b2 is 0, and when it's not equal to y, then b2 is positive because we are taking absolute value.
Yeah,
So metric
it will also be a metric. Yeah, we need to check it by the definition. So this is actually a very easy one. So D2 is metric. Let just write. D2 is a metric. So let me quickly check the axioms. D2 of xy is clearly non-negative because it's just modulus. But what happens when D2 of xy is 0? That means mod x plus mod y is 0. And this will be true if and only if mod x is 0 as well as mod y is 0. But sorry, I think D2 is not a metric because our set is open interval 0 1 and 0 is not in this set.
Sir, but they defined when x equal to y, the value should be metric should be 0. They defined as.
Yeah, but what happens if D2xy is 0? Can we conclude x equals to y?
Sir, they themselves given in the definition, the metric is defined in that way only. Whenever x equal
No,
to y,
it is
it,
if and only if. D prime is xy is 0 if and only if x equals to y. So I am talking about this direction. So did you get my point?
yes, sir.
Yeah. So D2 is not a metric. What I
Sir,
was saying
uh,
is wrong.
sir, I think the initial conditions hold, only triangle inequality doesn't hold.
So non-negativity holds.
Yes, sir, I think so.
So
Can
if
you please show the metric again?
yes. Yeah, this is the question.
Yes, sir. Distance between if
So
distance between x
if
and y is
D2xy
0,
is 0,
but if we assume that x is not equal to y,
yes,
then uh, either x is not 0 or y is not 0.
yes. No.
So
How can you say that?
Because x is not equal to y. So if both of them are 0, then they are equal.
So x not equals to y you are taking, and x y belongs to open interval 0 1.
Right. So if uh, x,
So mod x plus mod y cannot be 0, right?
uh, yes,
Because both modulus are positive.
yes.
Yeah. Yes. I was just confused.
I think even if it was not open interval 0 1, even if it was defined on R, it would work.
So it will be a metric on R.
Yes. Even then, non-negativity would work.
Sir, if we take d of 1 by 2, comma 1 by 2, then how it will work, sir?
D
d
of
of 1 by 2, comma 1 by 2.
yes.
Here x equal to y. But what about the distance? How they define?
Yeah, it's 1. It's not 0. So it's not a metric.
But 1 by 2 is equal to 1 by 2. So the distance is by definition 0.
Yeah,
Right?
we need to use this definition only.
Yes.
When the same point we are taking, it should be 0.
So all the conditions hold. I think just triangle inequality doesn't hold.
Okay, let's try to write down the things so that it will not mess up. So non-negativity for D2. So D2 of xy, this is clearly non-negative for all xy. But what happens when D2 of xy, one direction is clear, but D2 of xy is 0, but let x not equals to y. So this will imply x comma y belongs to open interval 0 1 and x not equals to y. So this means x is positive and y is also positive and they are not equal. So modulus of x plus modulus of y is positive. So this means d2 of xy is positive. So it is not 0. So this is a contradiction. So d2 of xy is 0 if and only if x equals to y, because the other direction is clear from the definition. So this is clear from definition. Okay, now symmetry will follow easily. This is trivial, but let's check the triangle inequality carefully. So d2 of xz, this is definition is mod x plus mod z, and this is 0 if x equals to z. Okay, so we are taking 3 points, x comma y comma z belongs to open interval 0 1. So how to prove this? So I think we need to put it in separate cases. So case 1, if x equals to z, then there is nothing to prove, right? Then all three things are 0. Then dxz, this is 0. This is clearly less equals to d of xy plus d of yz, because this is 0 and this thing is non-negative. Now x is not equals to z. So there will be two subcases. So one subcase is y is neither equals to x and y is neither equals to z. Then what we can do is dxz. This is mod x plus mod z. This is less equals to mod x plus mod y plus mod y plus mod z. Maybe it will be strict inequality because we are in the open interval 0 1. But we can club these things together. So this is this is d2. So this is d2yz. Okay, so far so good. And the other subcase, so y equals to x or y equals to z, but x is not equals to z. So this is same as mod x plus mod z. But if x equals to y, then d2xy is 0. So okay, so now this is, there will be two cases. This is mod y plus mod z if x equals to y, and if y equals to z, this is uh, mod x plus mod y. So this is d2y comma z, this is d2x comma y. So in both cases, this is less equals to the sum d2xy plus d2yz. We are getting the triangle inequality. So is it okay? Are you following? So it holds. So d2 is a metric.
So
Yeah.
what about the case when x y not y equal to x and y not equal to z? That case
So
will be possible.
so either x equals to y, means either y equals to x or y equals to z, right? Because x and z are not equal. So either this or this. So if y equals to x, then y cannot be equals to z because x is not equals to z. So in the first case, if y equals to x, then just we have this thing. This is d2yz. And in the other case, if y equals to z, then we have the other, exactly the opposite thing, d2xy. But both things are less equals to their sum. So are you getting?
Yes, sir. But little bit confusion that. Okay, sir. I will read again.
Yeah,
Then
maybe you just
okay.
try to do it on your own. And if you did not get, just see the notes. And if you still did not get, maybe you can come back in the next week. Okay, so both PQ are true. Yeah, any doubts? So the first option. Okay, I want to do some more problems. I want to do some problems related to the topology also. Okay, let's see how much I can do. So this is problem number 6. So this is from GATE 2025 and it is related to open balls. So we have already introduced open balls. So first let's write down the problem. So let X equals to the set of all ordered pair of real numbers, and let's say X equals to the, and X is the point written as x1 comma x2, Y is written as y1 comma y2. Let's define two metrics on R2. So d1 x comma y is just x1 minus y1 plus mod x2 minus y2. I think it was already defined in the lectures, but with different notations. And d2xy is just d1xy over 1 plus d1xy. So we have already seen that it is a metric. So now if the open ball around the origin of radius 1 by 7 with respect to the metric d1 is same as the open ball around the origin of radius 1 by alpha with respect to d2, then find the value of alpha. Okay, so here the set is R2 and we have defined two metrics on R2. I think this is the taxicab metric on R2 and this is dy1 plus d of this form. We have already defined it. So both are metrics on R2. Now the question is, if the open ball around the origin of radius 1 by 7 with respect to the first metric is same as the open ball around the origin of radius 1 by alpha, we need to find alpha. So let's recall the definition of open ball. So if you have a metric space x comma d and if you take a point x and a radius r, then the open ball is bxr or specifically bd of xr. And what is this? This is y belongs to x such that the distance from x is less than r. Right? This is the definition. So this is open ball at x of radius r with respect to d. So in our case, open ball around 0, 0 of radius 1 by 7. So what is this? So b 0, 0 radius 1 by 7 with respect to d1 is same as b with respect to d2 of 0, 0, 1 by alpha. So this is given. and d1 and d2 are defined. We need to find the value of alpha. So can you see?
Sir, alpha is equal to 8.
But how?
Um, if we find distance between y1 comma y2 and 0 0 with respect to d1,
Okay.
then it is absolute value of y1 plus absolute value of y2.
Yes.
And with respect to d2, it will be absolute value of y1 plus absolute value of y2 over 1 plus absolute value of y1 plus absolute value of y2.
Yes.
Um, if we put alpha is equal to 8, then uh, both both the balls are same. The equations are same.
Yeah, you are correct. But let's do the computation here. It's not difficult. So let's write this B D2 ball. How this set looks like. It's fairly easier. We just need to write down the things carefully. So by definition, this is all uh, points from R2 such that D2 of, so all points x comma y whose distance from the origin is less than 1 by alpha. Right, this is the definition. But what is this? This is all order pair from R2 such that this is D1 of 0 comma 0 comma xy over 1 plus d1 of 0 comma 0 comma xy. This is less than 1 by alpha, right? Now let's rewrite this. Let's simplify this. So this is alpha times d1 of 0 comma 0 comma xy less than 1 plus d1 of 0 comma 0 comma xy, right? So this is specifically, so let's take this d to left hand side. Then what we will get? This is alpha minus 1 times d1 of 0 0 comma xy is less than 1. So we can write this as d1 of 0 comma 0 of xy less than 1 by alpha minus 1, right? But what is this? This is the open ball around 0 0 of radius 1 by alpha minus 1 with respect to d1. So are you following? But what is given? This is same as 1 by 7. So this implies 1 by alpha minus 1 is same as 1 by 7. So alpha minus 1 is 7 and alpha is 8. So you just need to do the computations carefully. This is not a big deal. Okay, any doubts so far?
No, sir.
Okay. Okay, maybe let's do some on the topology side. This was problem number 6. So this is not a problem but an example. Uh, so there is already several examples in the lectures, but I want to introduce this example of a topological space because this example will be useful sometimes in giving counter examples. So this is known as Sierpinski space. So how it is defined? So this set is just consist of 0 and 1, and on this set I will define a topology as it is just empty set X and singleton 0. Then clearly you can check that it is a topology. And it has some interesting properties. Maybe I will come back later when we will define continuous functions. But you can see that the only open set, so open set means elements of the topology. So only open set containing 1 is the whole set X. So this space is known as Sierpinski space. So it has some interesting properties. I will come back later because we have not done much of topological spaces. But one more thing is important here is Sierpinskification. So let me just mention this. So from a given topological space, I will create one more topological space. So let x comma tau be a topological space, and let star be a point disjoint from the elements of X. Okay, now consider let's say X prime as X union star, or sometimes people use disjoint union like X disjoint union star, but let's not confuse ourselves for the time being, and define tau prime as tau union this singleton point. Sorry, not singleton point, my bad. X prime. Then you can check this tau prime is a topology on X prime. Tau prime is a topology on X prime. And what is the speciality of this? Here, the only open set in tau prime that contains star is X prime. So this point star is called a Sierpinski's point. This point is called a Sierpinski point because only the whole set uh, contains this point, because there is no other open set which contains star. So this is some terminology that I want to mention. This part, this Sierpinskification might not be useful, but this example we might use later. Okay. Okay, let's do one problem now. Problem number 7. Then we will stop. So if we have a finite set X, if X is a finite set,
Sir, in a self-intensification, the star point we are going to get from outside of the set.
yes,
Okay, okay, sir. Means which is not in the set. Since 0 and
yeah,
1 are the only two points present in that set, the topology,
yes,
Sierpinski. But
yes,
we are getting outside one point and then we are defining something.
yes, we are taking a point which is not in X, then we are adjoining that point to X.
Okay, okay, sir. Thank you, sir.
Yes. So what I was saying, yes. So if you have a set X which is finite, then a topology tau on X means tau is a subset of the power set of X, right? By definition. So how many topologies can we define? We can define in a finite set. That is finite, right? Finite number of topologies. Because cardinality of power set of X is also finite. So yes,
Means for each open set we are going to define one.
sorry.
Sir, for each subset we are going to define a topology and we can make open sets singleton and some other which has been in the format of. In that reason only you are saying the topologies we are going to get also finite. Since the power set
Okay,
is
let me
finite.
let me say this very specifically. Okay, so maybe this can be put as a discussion here. So let X be a finite set. Now, if tau is a topology on X, then tau is basically a subset of the power set by definition, right? So that means tau belongs to the power set of X. But now cardinality of X is finite. So cardinality of power 6 is also finite, which is 2 to the power cardinality of X. So cardinality of power set of X, this is also finite. And tau is one of the members of that set. So you can have only finite number of topologies. Now is it clear?
Yes, sir.
So on X we can define only finitely many topologies. Okay, so finite on a finite set there can be only finitely many topologies. But what happens when X is infinite? So it's not that much important, but let's put this. What is the number? Forgot 7. So let X be an infinite set, then show that there exist infinitely many topologies on X. Okay, so on an infinite set you will get infinitely many topologies. So I hope you have understand the statement. So how to do this? So what I will do is I will explicitly create infinitely many topologies. And how I will do that? So since X is an infinite set, uh, X has a countably infinite subset. Okay, let's say x1, x2, or might be maybe in xn such that n belongs to the natural numbers. Okay, we can do that, right? So do you know how to do this, how to prove this? Yes, anyone?
Sir, every open ball on a set, every open ball on a set is ball.
Actually, your voice is not clear.
Sir, every open ball is also a topology. So I think using that we can.
Sorry, I'm not able to hear you clearly. Maybe you can write it in the chat box.
Sir, he is telling every open ball is an open set since there are infinitely many open balls. That format he is telling.
No,
But
I'm talking about the topology, not the open sets.
sir, since topology is how means we set is uncountably infinite, and the cardinality is alif naught. The power set will be 2 power alif naught. It will be C means the total open subsets what we are getting here will be
Yes.
C. So
So
we can form.
you are saying the cardinality of the power set is also infinite.
It will
So
be continuum, sir. Yes. After
yes,
that, we are going to get.
but all the subsets of the power set that need not be a topology, right?
Sir, but since we can, by taking each open set, I can form a topology. Means just like singleton B. If I take any
Yes,
natural
that
numbers,
is what I am going to do.
yes, sir.
But I am asking about this statement. Since X is infinite, it has a countably infinite subset.
Yes, sir. Every infinite set has a proper, proper countably infinite set.
Yeah, how to prove this statement?
Means when we are going to take, for suppose n, if I take means then I am going to remove one element one, and I can get the bijection map from 2, 3, 4, and so on, and same elements
No,
by
I'm saying
defining.
how to get this countably infinite subset from an infinite set.
Uh, Sir, since it is infinite, it is non-empty, so we can choose an element.
Yes, exactly. So you take just x1 from x. Now you
Then
take
we
x
can
minus
remove it.
x1. Yes, and this is infinite. So you can take x2 from this. So you got x1 and x2. Now you remove x1 as well as x2. This is also infinite. So you take x3 and you add it. Now you remove x1, x2, x3. This is also infinite. And you just continue this process. So then you will get a countably infinite subset. It's very easy actually. Now using
Uh,
this, I will define tau n as phi x and just xn. Then each tau n is a topology on x. Then each tau n is a topology on x. So there are infinitely many topologies on X. So we are basically using this statement. Okay. So maybe I think we can stop here. So is it okay, or you have any other questions from the lectures?
Uh, Sir, for the countably infinite set part, how
Yes.
can we do it a bit more formally, a bit more precisely, maybe?
How means?
The act of choosing elements one by one means you take one element or and remove that,
Yes.
and again take one element. So is it a recursive procedure? Like
Yeah,
how
it is
make
an
it more
inductive
precise?
process actually. So by some kind of induction, yes, you can
Yes,
do it
sir.
inductively.
Uh, that only I wasn't sure how to do it. Maybe I guess it requires the axiom of choice.
I think I don't think we need that, because we are taking an element from a non-empty set,
Yes,
and it will never be empty, because if we remove a finite set from an infinite set, it will still be infinite. So we are
right.
just doing induction.
Yes, sir.
Yeah.
Actually, I was studying one book and the same problem was present there, and it said it requires the axiom of choice. So
Oh,
I
is
couldn't
it
do it.
so? Maybe then I need to think it. Yeah, maybe I need to think it more carefully then. Okay, maybe I will check it later.
Yes, sir. Thank you, sir.
Yeah, okay. Okay, any other questions?
Sir, for the Sir, for the definition of a topology, we usually take a non-empty set. But
Yes.
if we try to define a topology on an empty set, like x is equal to 5, then and we take the topology T as a set of 5, then it satisfies all the three properties of topology. So why is it not a valid topology?
But what we will do with that information? Is it something useful? I think that is not a much useful idea, right? So that's why I think people avoid the empty set.
So, but it satisfies all the properties of.
Yeah, it trivially satisfies, but it will not give anything new.
Okay, okay, sir. Thank you, sir.
Maybe I'm not an expert in this topic, so maybe I need to check. Yeah. Okay, anything else? Okay.
No doubt, sir.
Okay. So if there is no other questions, maybe I will stop here, and we'll meet in the next week again in the same time. So meanwhile, try to see the lectures, and if you have any doubts, you can also write in the discussion forum, and you can ask in the next live session also. So, okay, have a good day.